This article has been accepted for publication in a future issue of this journal, but has not been fully edited. Content may change prior to final publication. Citation information: DOI 10.1109/TVCG.2019.2929033, i.e. Journal OF TVCG, Volume 20, NO. X, month 2019. Direct selection. Filtering elements can be the direct result of a selection action. The Virtual Data Visualizer, 39, the Cosmic Explorer, 139, as well as the system of DeHaan et al., 36, 140, triggered a filtering action upon box selection completion, hiding any data point outside of the box. Slicing of the 3D model is often allowed in medical imaging. In Zhang et al.'s system, 128, the slice position was determined by the displacement of the wand while pressing a button, resulting in hiding the 3D model parts outside of the slice. Laviola Jr. et al. CFD's system, 34, allowed the removal of any particle injector, hence the related data points, by placing the data glove near it and using the voice command remove. Abstract layer. Menus can be used to filter objects without prior selection. 582 and iFlight 94 both used a 3D raycasting menu selection to toggle the display of trajectories based on categorical attributes. NeuroCave 65 offered a similar functionality with a classical 2D WIMP interface on the supportive 2D display. Genome 3D Explorer 115 offered to filter visual elements such as nodes, edges, or labels through voice commands, hide nodes, or show labels. IDEA 75 displayed a menu on top of a physical tablet attached to a roller chair, bringing haptic feedback to menu selection. The query was then materialized by a selection cube that could be activated or deactivated at will to filter data. Jackson et al. 134 proposed a tangible controller for their visualization of thin fiber structures with the form of a long thin cylinder made from rolled paper. The 3D orientation of the cylinder allowed the filtering out of any fiber not sharing the same orientation based on a user-defined angle threshold. The interactive slice WM64 allowed the definition of a complex hull on a 2D slice with a multi-touch screen, and any streamline going through it was made apparent. Last, Herder et al. 148 proposed to link the filter threshold for a numerical attribute directly to the user body position in a room. Therefore, they used one dimension of the room as a slider, and its position was determined by the user's physical position. For point 7 aggregate, annotate, import, derive, and record. All remaining low-level interaction tasks are regrouped here, since they are far less common in IA literature. The aggregate task covers interactions that change the granularity of visualization elements. Herder et al. 148 employed an edge bundling technique for their 2D graph visualization using the Microsoft HoloLens. The users could change the force coefficient of the edge bundling algorithm from weak to strong by moving their bodies in the room over a virtual line. The annotate task covers interactions allowing users to add graphical or textual annotations to the visualization. The Network Visualization System Besno SDIS 149 proposed to associate text notes to selected elements, nodes, or edges by integrating a physical keyboard into the virtual world. Tagger VR 150 allowed users to select slices of one of the views and associate some predefined tags to it through hand gestures captured via leap motion. The import task covers the addition or the replacement of data elements from new data sources. The Archaeological Vita System 42 allowed users to import 3D models of a 11. Discovered artifact by grabbing them out of a 2D screen, directly putting data gloves in contact with the 2D screen and performing a closing fist motion. NeuroCave 65 let the user switch datasets from within the HMD, but no further details were given. The derive task covers the computation of new data elements from already available data. No paper in our corpus referred to such interactions. The record task covers interactions designed to capture visualization elements, or interaction logs. Undo actions were available in the Virtual Data Visualizer 39 through 3D menu raycasting selection. VRGobi 29 used an equivalent menu to save the visualization state, color, shape, and size of each glyph in a text file. Drawhard et al. S. System 151-152 allowed users to save their current positions and orientations in the virtual world, also in a text file. However, no detail was provided on how the IA system state could be loaded from such files. Last, Laviola Jr. et al. 34 proposed to record a snapshot and a video of the visualization with voice commands, respectively using Remember This View and Recording. The saved view could then be accessed through the voice command Show Me the Saved View and the video with the voice command Playback. One limitation was that only the last recording could be accessed. For Point 8 discussion. Two interaction modalities dominate: raycast selection with a controller and virtual tool metaphor. Raycast selection is an attempt to convert the classical mouse pointing of 2D interfaces to a 3D world and provides the advantage of not limiting the distance at which the user interacts, even though the farther the object is, the harder it is to point at it. The virtual tool metaphor aims to emulate the natural interactions of humans in daily life by using tools to perform specific actions. Though IA is defined as a multimodal experience by Chandler et al., other interaction modalities are underrepresented. For instance, only a few systems make use of speech. Also, there is a lack of guidelines and best practices for interaction in IA. However, this may be changing, as illustrated by two recent works. Badham et al. 155 proposed an affordance table of interaction modalities for low-level tasks, and there is a whole chapter dedicated to interaction. 156 in the IA. Book published in 2018, 157, where the interested reader may find valuable resources for IA system design. This leads us to an important conclusion for IA research. So far, only basic interactions have been used in IA systems, while VR, AR, and 3D UI community literature is full of innovative means to perform 3D interactions, together with best practices. Such knowledge would most likely benefit IA systems design. Few remarks can be added. First, navigation design needs to consider cybersickness. 149. IA systems are meant to be used for extended periods of time, and user comfort is very important. 158. However, such comfort is often overlooked in papers, even when smooth locomotion is used. Second, IA allows large-scale data worlds to be explored, but context-aware navigation techniques such as WIM are not exploited enough, even though they are critical for the user. 41. And last, IA systems tend to overlook supportive. This article has been accepted for publication in a future issue of this journal, but has not been fully edited. Content may change prior to final publication. Citation information: DOI 10.1109/TVCG.2019.29290033, IE Journal OF TVCG, Volume 20, NO. X, month 2019. Low-level tasks, IE aggregate, annotate, import, derive, and record, which nevertheless continue to be needed if full-fledged data analysis systems are to be built. Collaboration in Immersive Analytics. Collaborative Immersive Analytics, CIA, is defined as the shared use of immersive interaction and display technologies by more than one person for supporting collaborative analytical reasoning and decision-making in the CIA section of 159. This section discusses the collaboration-related features of the 15 CIA systems in our corpus. It can serve as an IA system-oriented prologue to 159. We describe how users interact with each other, focusing first on systems that allow physical interaction, and then on those that use virtual representations of users. We chose this presentation over the usual same versus different place categorization because IA systems bring additional complexity. Users can be in the same physical space, but have different virtual representations, or on the contrary, be in different physical spaces, but within the same virtual environment. 5.1 Physical Collaboration. Physical collaboration in IA started by placing multiple users in the same room using the same virtual reality technology, e.g. multiple users in front of a fish tank, 71, a workbench, 33, 81, or inside a cave, 128. This has the advantage of letting users interact naturally, but presents the major drawback of providing a correct representation of the virtual world only for the head-tracked user. Gestural communication is also impacted since finger pointing to show a point of interest cannot work in this context. One solution proposed by 128 is to use a controller to project a raycast for finger pointing. Another solution is to head-track multiple users as seen earlier for Agrawala et al. 37, Workbench. The new generation of Cave was designed from the beginning for CIA 27. For instance, Cave 2 was built to allow any collaborator to share flawlessly individually owned data with the group by displaying it either through classical 2D representations or via the immersive envy. Ronmint. Cave 2 offers the possibility to visualize mixed views, where a part of the screen is dedicated to immersive representations and the other to 2D ones. Such choice to decrease immersion was made to improve collaboration because, according to the authors, it is at best extremely difficult to integrate multiple useful representations into the same virtual world, and multiple representations can often be better than a single shared representation, 160. Augmented reality technology has also been used to provide physical collaborative IA. In 2004, VITA 42 allowed multiple archaeologists to enter the same virtual representation of an excavation site in AR. Users reported enjoying the interaction with their colleagues in a direct manner, but stated that the AR glasses were hiding the collaborators' eyes, causing a discomfort in the interaction. In their system to prevent maritime smuggling, Franz et al. 55 used the Microsoft HoloLens combined with a tangible map of the shore. This representation allowed all the users to share the same position of entities, allowing quick finger pointing gestures to share objects or potential movement strategies. 12. While allowing each user the freedom to have individual additional information displayed on the headsets. Butcher et al. 110 proposed a similar solution, using a touch table as the central point of representation and a headset for each user. The same virtual world was shared among all users and all interactions were done using the multi-touch table. Last, the principle of datatar has been presented by Chen et al. 16 as a combination of the words data and avatar. Each user/datatar embodied one tuple of a multidimensional dataset and had to collaborate with other datatars to solve dimension reduction problems. 5.2 Virtual Collaboration. Virtual collaboration gathers users from different physical places who are connected to the same IA session through various hardware. The earliest work was the distributed virtual wind tunnel in 1992-21. Two users could connect to the same representation of CFD simulation, each using a boom. The system allowed users to leave or join the session at any time. Conflicts were solved on a first-come first-served basis, preventing, for example, users moving the same particle injector at the same time. The Cave 6D88, 89, and the Tide 131 systems allowed connection between Cave and Workbench users. Both proposals focused on interdisciplinary analysis of oceanographic and climate data. Users communicated directly via a voice chat and with gestures. Each user was represented by a simple avatar composed of a head and a hand, both following the tracked user's movements. A raycast was attached to the user's hand to facilitate pinpointing locations. A characteristic of the Cave 6 was the ability to let each user filter parameters, either locally, affecting only his visualization, or globally, affecting everyone's visualization. This led to positive feedback from users, since they were able to investigate the data without disturbing their collaborators before sharing it with them. Cordell et al. 93 used HMDs in their plane trajectory analysis system to connect users to the same virtual world. Leap Motion was used to provide virtual avatars with complete hands, letting users compose with a broader freedom for nonverbal communication. Last, MICA, Meta Institute for Computational Astrophysics, experimented with the Second Life social virtual world as a way to connect people for data analysis. 15. E.g., the analysis of the output of a dynamical simulation of a star cluster. The main goal was to see the impact of virtual environment as an educational and outreach platform, and the platform could be used without any requirement other than a Second Life account. Feedback from users was highly positive, but it was not enough to ensure their return on a regular basis. 5.3 Discussion. We have two main conclusions. First, only 15 papers out of the 127 system papers in our corpus have focus on collaboration, which represents less than 12%, though collaboration is defined as a critical component for the success of IA. 161, 162. Second, no asynchronous collaborative system is mentioned, leaving a whole area unexplored. This point may be explained by a lack of attention to low-level interaction tasks required for asynchronous collaboration, such as annotate and record. This article has been accepted for publication in a future issue of this journal, but has not been fully edited. Content may change prior to final publication. Citation information: DOI 10.1109/TVCG.2019.2929033, i.e. Journal OF TVCG, Volume 20, NO. X, month 2019. Immersive Analytics User Studies. The second main category of papers in our corpus is related to evaluation. 28 papers focus on IA systems evaluation. 26 compare IA and non-IA solutions, and 14 compare technologies. 5 interaction solutions, 7 or representations, 2 within the same IA system. This section is organized along this subdivision. 6.1 Evaluating IA systems. The most common way to evaluate an IA system in our corpus is by gathering feedback from users while or after they have used the system. In general, domain expert users participated in the studies when available. 12 papers used an informal evaluation approach where final users were invited to use the system. In some cases, they had participated in the design process. Kerr Ugger et al. 33 asked doctors, engineers, and architects to validate their initial concept of the responsive workbench, obtaining suggestions for improvements, such as adding haptic feedback for the medical application, or increasing resolution for the industrial one. The virtual data virtualizer was used by computational physicists, and the VR depiction was considered more real and immediate than a workstation display. 39. AI et al. 80 received positive feedback for their molecule analysis system, which was deemed to be close to using real plastic models. Zhang et al. 128 had positive comments from doctors and senior medical students about the ease of use of their system. Henschel et al. System 85 collected user feedback to define the type of visualization needed for blood damage analysis. The BIMA system 135 was used by an ancient Greek rhetoric and oratory scholar to obtain insights into political assemblies at the Knicks. This specialist stated that his experience had given him a lot of confidence in what this showed, compared to using his imagination or pictures. VR Miner 106 was used by biostatisticians and dermatologists who appreciated its features for detecting correlations between skin photographs and other data dimensions, checking the quality of discovered clusters, and presenting the data to a panel of experts. Using the Cave 2, experts expressed that it allowed them to get more done in 2 days than in 6 months of email, Skype, and Google Hangout 160. GBR Tour 54 received feedback about the lack of resolution of their system and the need to improve navigation. Fury et al. 115 genomic database IA system was used by biologists, but they give no precision on the gathered feedback. Cunningham et al. 96 invited 3 experts to use their visualization of law enforcement. Narratives. The think aloud feedback they collected showed, for instance, that the visualization was not as crowded in VR and much more understandable than usual tools. An informal evaluation approach with non-domain expert users was also used, e.g., 34 gathered feedback from a number of people who said that voice command was great but gets annoying when commands are not recognized, especially in a noisy environment. Reddy et al. 95 enrolled people from their laboratory that had never seen their system before. The feedback was that it was not intuitive initially, but became great to use after some training and explanation. 12 papers used a formal evaluation approach with dedicated sessions, 7 of them with domain expert users. 13 sessions all had the same structure: system introduction, training on the main features of the system, a set of tasks to be performed, and questionnaire and/or interview. However, the evaluation objectives differed between studies, leading to different tasks. When expert users were available, the objective was to determine the usefulness of the system for data analysis, so experts had the freedom to explore interaction and analyze data as they saw fit. For instance, Archive was evaluated by 2 groups of archaeologists, the first one willing to analyze the lamp finds in the Petra Temple, while the second wanted to explore the relation between the temple and the neighboring ancient sites, 66. 67. For the formal evaluation of the Vita system, archaeologists were asked what they intended to investigate prior to the evaluation session, and the tasks were designed accordingly, 42. Helbig et al. 101, Cantu et al. 77, Butcher et al. 110, and Herder et al. 98 also let users freely use their IA system. When evaluation was conducted with non-expert users, the goal was to evaluate the usability of the interactions. In this case, the choice was made to guide users who had no experience in the dataset by precisely defining the tasks to perform, such as in the wizard. 41. Interactive Slice WM. 64. Explorviz. 125. Idea. 75. And Saalfeld et al. S. 69. Systems evaluations. 3 systems succeeded in reaching the milestone of being used in real work environments. The Dragon system was used during 2 training military operations. The Hunter-Warrior Advanced Warfighting Experiment in March 1997 and the Joint Counter-Mine Advanced Concept Tactical Demonstration in August and September 1997, 35. The artifact Vis-2 was extensively used to analyze an Iron Age site in southern Jordan during the entire duration of the excavation project, 68. Jackson et al. System, 134, was used in their lab by the 2 biophotonic experts that collaborated in its development. Our last system evaluation paper is more difficult to categorize. Furman et al. 40 make strong claims about their AR system, such as enhanced interaction capabilities or reduced abstraction, but provide no details of their evaluation or how such conclusions have been reached. 6.2 Questioning the benefits of immersion. The potential benefits of IA over non-immersive solutions appear to be dependent of data types. We will successively focus on graph, multidimensional, and spatial data. Let us state that there was no evaluation paper in our corpus directly comparing immersive and non-immersive solutions for temporal, spatiotemporal, or tree data. A summary of the findings can be found in Table 3. Graphs. 3D representations have long been disregarded in the graph community, as it was considered they had significant problems mainly due to perceptive and navigational conflicts when exploring 3D worlds using 2D interfaces and screens. 163. Immersive environments were also disregarded for the same reason. It can, however, be argued that IE provide very different experiences by offering their users true 3D together with embodied interaction, and that it is, therefore, not possible to apply previous conclusions to IE systems. 158. Where et al. 32, 164, 165 consistently proved the benefits of IA systems for network visualization. They performed. This article has been accepted for publication in a future issue of this journal, but has not been fully edited. Content may change prior to final publication. Citation information: DOI 10.1109/TVCG.2019.29299033, IE Journal OF TVCG, Volume 20, NO. X, month 2019. Multiple user studies comparing 2D with 3D stereo, simple head tracking, or both combined, fish tank visualizations. For instance, users were asked to determine if a path of length 2 was connecting two highlighted nodes for varying graph sizes, 24 to 132 nodes. The results showed that the error rates were proportional to the number of nodes. The fish tank could display 3 times the number of nodes of the 2D solution before reaching the same error rate, while head tracking alone brought this number down to 2.2 and stereo alone to 1.6. In 2008, a new study used the same principles, 166. The resolution of the screen was brought up to 9.2 million pixels per eye to display image at the limit of the resolution of the human eye. For graph size conditions were considered 33, 100, 333, and 1,000 nodes. The results showed that non-experienced users were able to achieve a 92% accuracy using IA with the 333 nodes condition, while experts achieved 90% accuracy for 1,000 nodes. Similar accuracy was only reached by non-experts. In 2D with 33 nodes, Belcher et al. 114 used the same protocol as the early-ware studies, i.e. same tasks, and 21 to 75 nodes. The main difference in their study was that they compared 2D, 3D, and AR solutions. The graph was displayed on top of a disk with a fiducial marker. AR and 3D solutions proved significantly more accurate, but this result must be mitigated since the 2D solution was a projection of the 3D solution with no possibility to rotate the graph, while it was possible in the two other conditions. Grefford et al. 167 compared 2D with 3D stereo with no head tracking for node/link representation, resulting in the 2D solution being better for simple graph, but 3D stereo being better for complex graph. Samavati et al. 168 compared a wall no stereo, no head tracking to a Cave4 wall for multiple tasks such as intersection search, path following, connection identification, and length comparison. The results showed significantly greater accuracy for intersection search and connection identification for the IA solution, but no difference for length comparison tasks. Multidimensional data. 3D representations have been explored very early, but most researchers have long disregarded the use of 3D, considering that 2D conventional techniques were sufficient for typical tasks related to pattern, trend, or outlier discovery. 169. Immersive technologies, however, bring in a new type of 3D together with embodied interactions, which is worth exploring. Wickens et al. 170 compared 2D and 3D scatter plotting in 1994 using a 3D stereo screen, resulting in better accuracy and completion times for 3D scatter plots for complex questions such as, which data points have the highest value on all three variables? However, it is important to note that the dataset only consisted of 8 points. XGobi, a desktop system, and VRGobi, a cave system, aimed at analyzing multidimensional data with 2D or 3D scatter plots and grand tour technique, permanent revolution of the representation around a vertical axis. 171 have been compared in 172. VRGobi showed significantly better accuracy for cluster identification tasks on datasets ranging from 74 to 500 tuples. Raja et al. 173 compared multiple systems for 3D scatterplot representation using for field of regard and HT head tracking as independent variables. Tasks covered search, cluster, outlier, and trend detection. The combination of higher for and H significantly diminished. 14. Completion times. Another study focused on the impact of for Yost et al. 133 compared a 2MP with a 32MP screen for search and trend determination tasks using a multi-view representation. Each view kept the same scale in both conditions. Therefore, the 32MP condition displayed an enhanced number of views. Increasing the dataset size by a factor of 20, both in dimensions and tuples, for the higher for condition, i.e. 32MP screen, resulted only in a 3 times increase in completion time with no significant effect on accuracy. Filio et al. 174 compared two-dimensionally reduced data scatter plot representations, 2D on a screen, 3D in a VR HMD, for the analysis of the original dataset with search and outlier discovery tasks. Results showed that IA was both the most accurate and the most engaging, while desktop remained the fastest and the most intuitive. These results show that IA may be beneficial even for abstract visualization. Last, Bach et al. 175 compared Microsoft HoloLens AR, tablet AR, and desktop for the analysis of dense 3D scatter plots. The tablet was the worst performing solution for all tasks, and participants agreed. For distance evaluation tasks, desktop was faster than HoloLens with no impact on accuracy. For cluster identification and selection tasks, desktop was the fastest, but HoloLens was the most accurate. For plane cutting tasks, HoloLens was the fastest and hinted on a better accuracy than desktop. Participants preferred desktop for manipulation and the HoloLens for perception. Spatial data naturally benefits from 3D representations as it is inherently 3D. Therefore, the main question is to explore what benefits immersive 3D can bring over 3D displayed on 2D screens. The earliest user study on spatial data in our corpus was from Gurchala et al. In 2004, 176. The study compared users trying to position an oil well over an oil field using either a 2D desktop or a cave. Cave proved to be significantly faster and more accurate. Similar results were found in the inspection of underground caves. Schuchart et al. 177 found that for detailed search tasks, identify cave connection, or relative measurement tasks, compare the sizes of caves. Cave performed significantly faster and more accurately than 2D. Focusing on the same type of data, Reagan et al. 178 went a step further, considering field of regard for total area available to the user to see the representation, stereo, ST, and head tracking, HT, as independent variables. For was controlled by using 1 or 4 cave walls, while ST and HT were turned on and off. For and HT combined improved accuracy, while the combination of HT and ST improved completion time. Van Schuten et al. 179 use stereo and motion as independent variables for a study on maze structured data representation. Participants had to follow one particular path through the maze. Motion was simply the ability to control the panning and rotation of the representation. It proved to significantly increase the completion speed. Interestingly, stereo provided benefits over non-stereo only when associated to motion. Reagan et al. 180 also used an underground cave system for their study, with multiple attributes being displayed throughout the cave, e.g. ground density, with 3D bar charts. They compared a high-fidelity cave 4-wall with ST and HT, set up with a low-fidelity cave 1-wall, no ST, no HT, 1. The task was to find the highest value of a component inside. This article has been accepted for publication in a future issue of this journal, but has not been fully edited. Content may change prior to final publication. Citation information: DOI 10.1109/TVCG.2019.2929033, i.e. Journal OF TVCG, Volume 20, NO. X, month 2019. The cave, the high-fidelity condition was the fastest and the most accurate. For medical imaging, Laha et al. 181, 182 showed that for an HT improved accuracy, but did not find significant effects for completion time. In addition, Prabhat et al. 183 obtained better accuracy for cave over 2D desktop for confocal microscopy data analysis. One study did not demonstrate the benefit of immersive solution for spatial data, 184. However, only 2 sizes of screens and ST were investigated, and HT was not available despite its critical importance for IA. To conclude, there seems to be concurring evidence that IA provides benefits over non-IA for the analysis of graph and spatial data when the complexity of the scene exceeds the limits of 2D displays. Results for multidimensional data are more mitigated depending on the tasks. 6.3 Assessing technologies, interaction or visualization techniques. Technology. The availability of numerous immersive technologies has led researchers to try and determine which were better suited for IA, especially when some of them, like the cave, are a lot more expensive than others. Demorap et al. 185 compared a fish tank with a cave for visual search tasks in a stream tube representation of the human brain. Fish tank was significantly faster and more accurate, and users reported their preference for its increased brightness and resolution. However, the full model was always visible on the screen in the 2 conditions so as to lower the impact of the limited for a fish tank due to its small screen. Chi et al. 73 compared a fish tank with an HM for an overview visual search task in volumetric data. Fish tank was also found to be significantly faster and more accurate. However, users were placed inside the volume to be investigated when using HMD, while in fish tank they had an overview, all tasks being related to the investigation. Of the full volume, Laha et al. 186 compared to HMD with a cave to determine if both led to the same results for volume data analysis, hence allowing previous conclusions drawn with cave to be applied to HMD. The absence of significant differences is a step towards the validation of this hypothesis. Cordell et al. 187 compared the benefit of their Cave 2 solution with a VR HMD for collaborative analysis of graph data to see if the added cost of the Cave 2 was justified. The tasks were simple, such as finding the shortest path between 2 nodes, or counting the number of nodes. Both conditions led to similar accuracy and completion times. Last, Marino et al. 188 compared a city metaphor for software visualization that could be experienced in a VR HMDR with a 3D printed representation. Finding the outliers proved to be faster with the printed representation, but the immersive environment was significantly better for recollection of the insights. Interaction. Studies in comparing navigation techniques for IA systems have also been conducted. Henry et al. 116 compared egocentric, flying metaphor, C4.1, and allocentric, rotating the visualization. Navigation's techniques for a node/link representation displayed in a cave with no conclusive result. Simpson et al. 189 conducted a similar experiment in an HMD for the analysis of 3D scatter plots, comparing egocentric, walking physically around. 15. The visualization. To allocentric, rotating the visualization. Navigation for a 3D scatter plot. No significant differences were found in either, as success was mostly driven by user preferences, even though users with low spatial abilities performed better in the walking condition. Another study from Buskell et al. 190 compared egocentric and allocentric navigations by either moving physically around an augmented reality representation on a tablet or by moving it by touching the tablet. No conclusive result could be found from quantitative data, but participants preferred the egocentric solution. The egocentric versus allocentric navigation comparison from Coffey et al. 64 had a small difference. Egocentric navigation could be user-controlled or automatically animated with no user control. The controlled navigation was the most accurate while the animated one was the fastest. Zelasco et al. 117 compared 5 types of navigations while using an HMD in a seated position at A. Desk, gamepad, shake your head, SYH, leaning, walking. In place, WP and pedal. Walking metaphor, i.e. SYH and WP, were significantly slower than the others. Drogemuller et al. 191 compared 4 different navigation techniques for graph analysis using a VR HMD while standing up, teleportation, one-handed flying, two-handed flying, and world in miniature, WM. Two-handed flying was the fastest and most preferred solution for tasks purely based on navigation, but WAM was the most efficient solution for tasks that required an overview of the scene, as it helped users keep the context in sight. One paper, 145, studied the impact of 2 different input modalities for the arrange low-level task in a node/link representation on a stereo screen. Participants could move nodes and edges with gesture-based interaction or classical 3D mouse. Quantitative results showed no impact on accuracy, but for the most complex graph, the gesture condition was significantly faster. Qualitative results indicated a significant preference for gesture-based interaction. Visualization. 2 papers focused in 2018 on comparing visualization techniques within IA systems. Fonnet et al. 192 compared 3 representations of a Cartesian coordinate system for 3D scatter plots, 2D grid, 3D grid, and a metaphoric representation of an apartment hall. Participants had to find the coordinate values of highlighted points. No significant result was found for accuracy, but some users changed their behavior in the hall. They began to use their arms to measure distances. Yang et al. 97 compared various representations of trajectories over a 2D map, 2D straight lines, 2D curved lines, and 3D curved lines. The task was to define which trajectory was the longest for selected trajectories. 3D curved lines ended up being the most accurate solution, 2D straight lines being the fastest. 6.4 Discussion. First, IA system evaluation is not systematic in our corpus. Only 22% of the papers describing a system also describe its evaluation. Also, higher system fidelity, i.e. higher for, using ST or HT seems to bring benefits with regard to accuracy for complex tasks, especially for graph and spatial data, cf. Table 3. For completion times, however, results are more uncertain. System fidelity studies are also lacking when it comes to other data types such as temporal, spatiotemporal, or tree data. In addition, we only found a recent 1077 to 2626, c. 2019 IEEE. Personal use is permitted, but republication/redistribution requires IEEE permission. seep/www.ieee.publications_standards/publications/rights/indexed him for more information. This article has been accepted for publication in a future issue of this journal, but has not been fully edited. Content may change prior to final publication. Citation information: DOI 10.1109/TVCG.2019.2929033 IEEE Transactions on Visualization and Computer Graphics JOURNAL-OFTVCG VUELD XX NO did X month 2019-16 data type measure better than an immersive worse than an immersive 176 big for plus ST plus HT 177 big for plus ST plus HT detailed feature search and relative measurement 183 big for plus ST plus HT 184 big for 181 big for 182 big for ACC 178 big for HT 176 big for plus ST plus HT 184 big for ST 177 big for plus ST plus HT detailed feature search and relative measurement 178 ST plus HT spatial time 179 ST ACC temporal time ACC spatiotemporal time 29 big for plus ST plus HT clustering and radial sparseness 175 ST 172 big for plus ST plus HT clustering and radial sparseness 174 ST plus HT ACC 170 ST if question involve 3 or more attributes 133 big for 174 ST plus HT multidimensional time 175 ST plus HT ST 32 ST 167 ST for small graphs 164 ST plus HT, HT, ST, 165, ST plus HT, 114, ST plus HT, ST, 166, ST, 168, big for plus ST plus HT ACC, 167, ST for large graphs, 168, big for plus ST plus HT, 114. ST plus HT graph time 167 ST ACC tree time table 3 recapitulative établir benefits of immersive solutions compared to non-immersive ions. Significant results reorganized by data types in quantitative measures, accuracy, ACC, and completion time, time. 4. Field of regard, ST, stereoscopy, HT, head tracking. Study comparing different visual mappings 97, a fact that may explain the apparent lack of best practices for data representation in IE. Also, user studies and interaction modality as shape in limited to navigation tasks, with the only exception being 145. This may appear to limitus if real immersive autonomous systems are to be built. User studies need to cover most of the low-level tasks where reviewed in section 4. An explanation for this limitation may be that topics already covered in general VR papers. However, we could argue that the specific tasks related to data analysis require specific ways of interacting. 7 HISDO RICE-ALSU MMARYN CHALENGES concluded the survey at an historical summary of development of IA from its beginning 1991 until today, and a presentation of 3 main challenges. They complete the discussions we have provided in each section. 7.1 Historical Summary Immersive Analytics began 9th research teams that were building immersive technologies. Bryson's team for the Boom, Crew's Nearest Fourth Cave, Ware's Fourth Fish Tank VR, and Kruger's for the Responsive Workbench. During the late 90s, they were joined by our researchers when immersive technologists started to be adopted biothar laboratories. However, its huge costs drove a theosob data thought wash direct the funding sources, leading mostly to scientific visualization systems, e.g. CFD, chemistry, and climatology.at. The beginning of the century, technology remained heavily towards the cave, but application domains become a metaverse, with software visualization. Archaeology, visual data mining, or burn analysis. Canoni. Cal visualizations begin to gain a few domains, such as time differs for software visualization. This of 3D vector fields with a Sager for climatology, particle injectors and TOA 3 vector fields for CFD, or 3D scatter plots for visual data mining. The next decades on new generation soft technologies, second generation of CAVM morpho-fused in collaboration than immersion, Cave 2 and Theoreality Deck. Cheap VRHM d'associated to Wasto develop content, Unity 3D, the Talodman Labsto Hoint HII movement, and a new generation of HMDR devices renewing the interest for ARI after only a few attempts, 40, 42, 107, 124. These wide variety of both fast-evolving technologies and application domains may explain a small number of IA software framework proposals 3, since that these would have been useful only to a small amount of people and very quickly become obsolete. Control input devices did not greatly evolve. 6 degrees of freedom controllers remain as the universal solution, even 3-4 computational fluid dynamics, 193 Proposita framework. Offering streamliner ISO surface representations that allow Adrien. Interaction hardware batted, Vista FlowLib, 83, focus set in high performance rendering GAN Perl computing. The Geomi framework, 194, was dedicated to network data analysis. It provided numerous representations and a high-level plugin for immersive interaction. More recently, 162, propose a general architecture for number of distribute disrsto analyze data in a collaborative way. This article has been accepted for publication in a future issue of this journal, but has not been fully edited. Content may change prior to final publication. Citation information, DOI 10.1109/TVCG.2019.2929033, i.e. Journal OF TVCG, Volume 20, NO. X, month 2019. If their shapes have varied a great deal between wands, stylus, VR gamepads, or tracked gloves. This has led to 2 main ways of interacting with IA systems, either raycast menu selection or virtual tools metaphor where objects may be grabbed with controllers. However, only a few low-level interaction tasks have been targeted, and a lot are still missing, such as import, derive, annotate, record, and aggregate. It should also be noted that collaboration has always been considered important since the beginning of IA research, the first IA collaborative system appearing in 1992. However, as seen earlier, a striking fact is that only synchronous collaboration has been considered so far. Despite these 3 decades of research, IA has long lacked unity as a research area. As shown by the evaluation papers in our corpus, researchers have mainly focused on justifying the value of their systems with respect to non-immersive ones, from where in 1993-32 to the present day, 174. Rather than evaluating as a community what the best representations or interaction techniques could be. The first definition of IA was proposed in 2015-1 as a tentative to provide a unifying label around the use of emerging user interface technologies for creating more engaging and immersive experiences. 3 years later, the second definition, 2, focused on the use of engaging, embodied analysis tools to support data understanding and decision-making, shifting the core of IA from technology to embodied analysis. 7.2 Challenges. In this survey, we focused on immersive technology with an embodied stance related to our head tracking condition. We identified three main challenges for IA to develop as a unified research area. Foster multisensory and embodied interactive IA. Immersive environments provide the unique benefit of having fully immersed users, and the full potential of IA may not have been discovered yet. This calls both for new representations that engage all the senses of the users and new interaction paradigms that exploit full-body immersion to its full extent. First, most data representations focus on the visual channel, with a lack of proposals making use of sound and/or haptics. Also, many of the 3D data representations proposals are extensions of 2D ones. All those representations have proved useful, but are likely not to be the only possibilities in IE. Second, IA researchers may not have experimented sufficiently with interaction. Most interactions focus on 6 DoF controllers that are either used for raycast selection over virtual menu or to grab virtual tools. There is, however, no reason to limit to these types of interactions or controllers. As an example, single. Object selection may not only rely on simple raycast, and may benefit from the rich literature from VR and gaming community, 195, 196. As a matter of fact, taking into account 3D UI and VR findings, 197 seems mandatory to fully integrate the embodied interaction paradigm to the IAF yield. An interesting example is IMAX's 129, which allows users to create new representations by simply empowering them with the control of axis arrangement. Converge towards best practices. Work on IA began 3 decades ago, but the unifying term immersive ANA. 17. Lytics was only proposed 3 years ago. Access to immersive technology has long been limited to a few teams, as well as exchanges between a small number of experts of different types of systems, resulting in a lack of acknowledged best practices. To reach such goal, it seems to us that work must be largely shared, and by this we mean sharing the actual user's experiences. Indeed, research usually mainly focuses on sharing knowledge through words and images, but this may be insufficient for IA 198. As for any immersive system, IA systems must be experienced for peers to be able to understand their full extent, which calls for open sourcing IA systems, as did IMAX's 199 or toolkits, such as the recent DXR 200 and ITK 201, or at least sharing 3D videos of experiences. Another point is that only 14 papers in our corpus focused on assessing best solutions for IA, Section 6.3, and comparing rendering technologies or navigation techniques have been the only 2 focus points for over 20 years. Data representation as a whole, as well as low-level interaction tasks, with the exception of navigation, were not investigated in any of the evaluation papers in our corpus until 2017. This means that a large part of the IA's area is yet to be explored and defined, and that an alternative route to reach maturity is to systematically aim at evaluating and assessing the validity of IA systems components for representation, interaction, etc. Aim at real-life IA systems. Data analysis having become a major industry concern, combined with the fact that VR/AR technologies are entering the corporate world, might lead to a new interest in enterprise IA systems for. Therefore, it seems important for IA researchers to focus on real-life scenarios for systems they build. This means, as we have already seen, that these must integrate the full package of low-level interaction tasks defined by 18. Inspiration can come from other fields, such as the use of annotation in immersive environments for 3D CAD models, leading to the possibility of asynchronous collaboration. 203, 204. Additional considerations for the design of IA systems are also required, related to their integration in the workplace and in the workflows of data analysts. This calls for research on user comfort and session durations, interoperability of 2D and immersive applications, transitions between corporate and immersive worlds, etc. Such conclusions are in line with those proposed by Werner et al. 205-4. The immersive visualization community. This also calls for interdisciplinary work between IA, design, workplace, and cognitive ergonomics, CSCW, sociology of organization, etc., 206, as well as partnership with industry, 207. Conclusion. WEP presented a survey of immersive analytics as it emerges from the study of an extensive corpus covering 3 decades. We described 127 IA systems focusing on their technologies, usages, sensory mappings, low-level interactions tasks, and collaborative capacities. A companion website is available where each system is systematically described and illustrated. The second part of the paper was dedicated to evaluation in immersive analytics, as well as a discussion of the main challenges. 4. Well-funded startups have begun to appear, 202. This article has been accepted for publication in a future issue of this journal, but has not been fully edited. Content may change prior to final publication. Citation information: DOI 10.1109/TVCG.2019.29299033, IE Journal OF TVCG, Volume 20, NO. X month 2019. Acknowledgements. This work is part of the IDEA project, Immersive Data Exploration and Analysis, funded by the Pays de la Loire French region through the West Creative Industries Program. References: 1, 2, 3, 4, 5, 6, 7, 8, 9. T. Chandler, M. Cordell, T. Zaderna, T. Dwyer, J. Glowacki, C. Gonku, M. Klapperstock, K. Klein, K. Marriott, F. Schreiber, and E. Wilson, Immersive Analytics in Proc. Big Data Visual Analytics. Hobart, TAS, Australia, IEEE, September 2015, pages 1-8. T. Dwyer, K. Marriott, T. Eisenberg, K. Klein, N. Reisch and F. Schreiber, Immersive Analytics, An Introduction in Immersive Analytics. Springer, 2018, pages 12-34. M. A. Fisher-Keller, J. H. Friedman and J. W. Tukey, Prim, 9. An interactive multidimensional data display and analysis system in AC Scientific Computer Information Exchange Meeting, 1974. T. Dwyer, N. H. Reisch, K. Klein, W. Sturzlinger, B. Thomas, and T. Dwyer, Dagstall Seminar 16231 on Immersive Analytics, Schloss Dagstall, Dagstall, Report 6, 2016. K. Marriott, T. Ito, F. Schreiber, and U. W. Osner, shown and meeting number 074 on Immersive Analytics, NI Shonan, Tokyo, Report 2016-2, 2016. G. Dahan, B. Henschel, D. F. Keefe, and O. Kralos, Immersive Visualization Revisited, Challenges and Opportunities, in workshop at IEEE VR, California, U.S., 2012. B. Bach, S. Carpendale, C. Collins, R. Doxelt, T. Dwyer, and L. Bongshin, eds, Immersive Analytics, Exploring Future Interaction and Visualization Technologies for Data Analytics, Niagara Falls, Canada, 2016. B. Bach, M. Cordell, T. Dwyer, B. Lee, B. Socket, A. Endert, C. Collins, and S. Carpendale, eds, Immersive Analytics, Exploring Future Visualization and Interaction Technologies for Data Analytics, Phoenix, USA, October 2017. J. Chen, G. E. Marai, K. Marriott, F. Schreiber, and B. H. Thomas, eds. Immersive Analytics, IA. Greenville, South Carolina, USA, 2016. 10S. Bryson, Virtual Reality in Scientific Visualization, Communications of the ACM, Volume 39, Number 5, pages 62 to 71, May 1996. 11R. M. Simpson, J. J. Laviola, D. H. Laidlaw, A. S. Forsberg, and A. Van Dam, Immersive VR for Scientific Visualization, a Progress Report, IEEE Computer Graphics and Applications, Volume 20, Number 6, pages 26 to 52, 2000. 12. A. Van Dam, D. H. Laidlaw, and R. M. Simpson, Experiments in Immersive Virtual Reality for Scientific Visualization, Computers and Graphics, Volume 26, Number 4, pages 535 to 555, August 2002. 13. Z. Bensaid, F. Guillet, P. Richard, J. Blanchard, and F. Picaron. An overview of interaction techniques and 3D representations for data mining, applications of virtual reality, Volume in Tech, 2012. 14. S. Bryson and C. Levitt, The Virtual Wind Tunnel and Environment for the Exploration of Three-Dimensional Unsteady Flows in Preceding Visualization 91, 1991, pages 17 to 24. 15. S. G. Georgovsky, P. Hutt, R. Knopp, G. Longo, S. McMillan, E. Vesperini, C. Donalek, M. Graham, A. Mahabal, F. Sauer, C. White, and C. Lopez, The Mica Experiment, Astrophysics in Virtual Worlds, Proc. Of the Slactions 2012 International Research Conference on Virtual Worlds, pages 49 to 58, January 2013. 16. X. Chin, J. Z. Self, L. House, and C. North, Be the Data, A New Approach for Immersive Analytics, in Workshop on Immersive Analytics, Greenville, South Carolina, March 2016, pages 32 to 37. 17. B. Schneiderman, The Eyes Have It, A Task by Data Type Taxonomy for Information Visualizations, in Proceedings 1996 IEEE Symposium on Visual Languages, 1996, pages 336 to 343. 18. M. Bremer and T. Munzner, A Multi-Level Typology of Abstract Visualization Tasks, IEEE Transactions on Visualization and Computer Graphics, Volume 19, Number 12, pages 2376 to 2385, December 2013. 19. M. Slater, A Note on Presence Terminology, Presence Connect, Volume 3, 2003. 20. I. E. McDowell, M. T. Bolus, S. D. Piper, S. S. Fisher, and J. Humphreys. Implementation and integration of a counterbalance CRT-based stereoscopic display for interactive viewpoint control in virtual environment applications in PROC, SBI 1256, Stereoscopic Displays and Applications. Santa Clara, California, September 1990. 21. S. Bryson and M. Gerald Yamasaki, The Distributed Virtual Wind Tunnel, in Proceedings of the 1992 ACM/IEEE Conference on Supercomputing, 1992, pages 275 to 284. 18. 22. C. Krusnera, D. J. Sandin, and T. A. DeFanti, surround screen projection-based virtual reality, the design and implementation of the cave, in SIGGRAPH, Anaheim, California, 1993. Pages 135 to 142. 23C. Krusnera, J. Lee, M. Papka, C. Barnes, S. M. Cohen, S. Doss, R. Engelman, R. Hudson, T. Roy, L. Siegel, C. Vasilakis, T. A. DeFanti, and D. J. Sandin, Scientists in Wonderland. A report on visualization applications in the cave virtual reality environment in PROC, IEEE Research Properties in Virtual Reality Symposium, 1993, pages 59 to 66. 24. T. M. Roy, C. Krusnera, and T. A. DeFanti, Cosmic Worm in the Cave, Steering a High-Performance Computing Application from a Virtual Environment, Presence, Teleoperators and Virtual Environments, Volume 4. Number 2, pages 121 to 129, January 1995. 25. T. H. Ollerer, J. Kucheramorin, and X. Adrien, the Allosphere, a large-scale immersive surround view instrument in PROC, Workshop on Emerging Displays Technologies Images and Beyond. The Future of Displays and Interactin. San Diego, California, 2007, pages 1 to 7. 26. J. Thompson, J. Kucheramorin, M. Novak, D. Overholt, L. Putnam, G. Wakefield, and W. Smith, the Allobrain. An interactive, stereographic, 3D audio, immersive virtual world. In Journal of Human-Computer Studies, Volume 67, Number 11, pages 934 to 946, November 2009. 27. A. Fabretti, A. Nishimoto, T. Thigpen, J. Talandis, L. Long, J. D. Pirtle, T. Paterka, A. Verlo, M. Brown, D. Plepes, D. Sandin, L. Renambit, A. Johnson, and J. Lee, Cave 2, a hybrid reality environment for immersive simulation and information analysis in the engineering reality of virtual reality, Volume 8649, Burlingame, California, U.S., 2013. 28. C. Papadopoulos, K. Petkoff, A. E. Kaufman, and K. Mueller, The Reality Deck, an immersive gigapixel display, IEEE Computer Graphics and Applications, Volume 35, Number 1, pages 33 to 45, January 2015. 29. L. Arms, D. Cook, and C. Krusnera, The Benefits of Statistical Visualization in an Immersive Environment, in Proceedings IEEE Virtual Reality, IEEE Comput, SOC 1999, pages 88 to 95. 30. N. Osawa, K. Ase, and Y. Sugimoto, Immersive Graph Navigation Using Direct Manipulation and Gestures, in Proceedings of the ACM Symposium on Virtual Reality Software and Technology VRSD 2000. Seoul, Korea, ACM Press, 2000, pages 147 to 152. 31. C. Ware, K. Arthur, and K. S. Booth, Fish Tank Virtual Reality in PROC, SIGGRAPH Conference on Human Factors in Computing Systems, Amsterdam, the Netherlands, 1993, pages 37 to 42. 32. C. Ware, D. Hui, and G. Frank, Visualizing Object-Oriented Software in 3 Dimensions in PROC, Conference of the Center for Advanced Studies on Collaborative Research, Software Engineering Volume 1, Toronto, Ontario, Canada, 1993, pages 612 to 620. 33. W. Kruger, C. A. Bone, B. Froelich, H. Schuth, W. Strauss, and G. Wesk, The Responsive Workbench, A Virtual Work Environment, Computer, Volume 28, Number 7, pages 42 to 48, July 1995. 34. J. Laviola Jr., MSVT, a virtual reality-based multimodal scientific visualization tool, in 3rd IASTD International Conference on Computer Graphics and Imaging, 2000, pages 1 to 7. 35. J. Durbin, J. E.S. 2. J. Colbert, J. Crow, R. King, T. King, C. Scannell, Z. Wardle, and T. Welsh, Battlefield Visualization on the Responsive Workbench, in Proc, Conference on Visualization. North Carolina, USA, ACM Press, 1998, pages 463 to 466. 36. G. Dahan, M. Kutek, and F. H. Post, Towards Intuitive Exploration Tools for Data Visualization in VR, in Proceedings of the ACM Symposium on Virtual Reality Software and Technology VRSDO2. Hong Kong, China, ACM Press, 2002, page 105. 37. M. Agrawala, A. C. Beers, I. McDowell, B. F.R. Olich, M. Bolus, and P. Hanrahan, The Two-User Responsive Workbench, in Proc, 24th Annual Conference on Computer Graphics and Interactive Techniques, SIGGRAPH 97, Los Angeles, California, 1997, pages 327 to 332. 38. I. E. Sutherland, A Head-Mounted Three-Dimensional Display in a FIPS 68. Fall, Part 1, San Francisco, California, 1968, pages 757 to 764. 39. R. Van Talingen, W. Rybarski, and C. van der Mast, Virtual Data Visualizer, IEEE Transactions on Visualization and Computer Graphics, Volume 3, Number 1, pages 65 to 74. 1997. 40. A. Furman, H. L. Offelman, and D. Schmalstieg, Collaborative Augmented Reality, Exploring Dynamical Systems, in Proc, 8th Conference on Visualization, Phoenix, Arizona, 1997. Pages 459 to 462. 41. A. Dady, Experiments in the Use of Immersion for Information Visualization, PhD dissertation, Virginia Tech, 2002. 42. H. Banco, E. W. Eshok, and S. Feiner, Collaborative Mixed Reality Visualization of an Archaeological Excavation, in 3rd in Symposium on Mixed and Augmented Reality, 2004. Pages 132 to 140. 43. S. Marks, J. E. Estevez, and A. M. Connor, Towards the Holodeck, Fully Immersive Virtual Reality Visualization of Psi. This article has been accepted for publication in a future issue of this journal, but has not been fully edited. Content may change prior to final publication. Citation information: DOI 10.1109/TVCG.2019.2929033, i.e. Journal OF TVCG, Volume 20, NO. X, month 2019. Scientific and Engineering Data in Proc 29th in SANF on Image and Vision Computing New Zealand, Hamilton, NZ, 2014, pages 42 to 47. 44. Oculus Rift, https://www.oculus.com/rift/accessed 201,807 to 20. 45. HTC Vive, https www.vive.com/accessed July 20th, 2018. 46. Meta, http://www.metavision.com/accessed July 20th, 2018. 47. HoloLens, https://www.microsoft.com/enus/HoloLens, accessed July 20th, 2018. 48. A. Liu, J. Huang, S. Zhang, C. Wang, and W. Wang, Towards Mobile Immersive Analysis, a study of applications in Workshop on Immersive Analytics, Greenville, South Carolina, March 2016. Pages 25 to 30. 49. Leap Motion, https://www.leapmotion.com/accessed 201,807 to 20. 50. A. Moran, V. Gately, M. Hubble, and J. Kepner, Improving Big Data Visual Analytics with Interactive Virtual Reality in High Performance Extreme Computing Conference, September 2015, pages 1 to 6. 51. D. Her, J. Reinhardt, R. K.R. Ugger, G. Reina, and T. Ertl. Immersive Visual Analytics for Modular Factory Layout Planning in Immersive Analytics Workshop, Phoenix, USA, 2017, pages 1 to 5. 52. T. V. Billow and J. A. Cottam, Exploring the Use of Heuristics for Evaluation of an Immersive Analytics System in Immersive Analytics Workshop, Phoenix, USA, 2017, pages 1 to 5. 53K. Nagao, Y. Yi, C. Wang, I. Fujishiro, and K. L. Ma. Enabling Interactive Scientific Data Visualization and Analysis with See-Through Hmsanda Large Tiled Display in Workshop on Immersive Analytics, Greenville, South Carolina, March 2016, pages 1 to 6. 54. H. T. Nim, M. Wang, Y. Zhu, B. Sommer, F. Schreiber, S. E. Boyd, and S. J. Wang, Communicating the Effect of Human Behavior on the Great Barrier Reef via Mixed Reality Visualization in Big Data Visual Analytics BDVA, November 2016, pages 1 to 6. 55. J. Franz, J. Malik, D. Riley, and L. Nettle, More Than Blips on the Radar, Exploring Immersive Visualization for Maritime Decision-Making in Immersive Analytics Workshop, Phoenix, USA, October 2017, pages 1 to 4. 56. K. V. Nesbitt, A Classification of Multisensory Metaphors for Understanding Abstract Data in a Virtual Environment, in PROC, International Conference on Information Visualization, London, UK, 2000. Pages 493 to 498. 57. K. Rita, A. Fabretti, A. Knoll, J. Orsano, J. Lee, A. Johnson, M. E. Papka, and M. Harold, Visualizing Large, Heterogeneous Data in Hybrid Reality Environments, IEEE Computer Graphics and Applications, Volume 33, Number 4, pages 38 to 48, July 2013. 58. T. Mahmood, E. Butler, N. Davis, J. Huang, and A. Liu, Building Multiple Coordinated Spaces for Effective Immersive Analytics through Distributed Cognition. In 4th in SYMP on Big Data, Visual and Immersive Analytics, Konstanz, Germany, 2018, pages 119 to 129. 59. D. A. B. Hyde and T. R. Hall, VRGE, an immersive visualization application for the geosciences in IEEE Civis 2018, Short Paper Session No. October, Berlin, Germany, 2018, pages 1 to 5. 60J, Nis, J, P, Schulz, U, W. Osner, P. Winkler, U, Lang, and C. Hansen, Medical Applications of Multi-Field Volume Rendering and VR Techniques in Proc 6th Eurographics. IEEE TCVG SANF on Visualization, Constance, Germany, 2004, pages 249 to 254. 61A. Gillett, M. Sanner, D. Stoffler, and A. Olson, Tangible Interfaces for Structural Molecular Biology. Structure, Volume 13, Number 3, pages 483 to 491. March 2005. 62. R. Shin, P. Boulanger, and M. Noga Medvis. A real-time immersive visualization environment for the exploration of medical volumetric data in 5th INT Conference on Biomedical Visualization, London, UK. July 2008, pages 63 to 68. 63. B. Chin, J. Moreland, and J. Zhang, Human Brain Functional MRI and DTI Visualization with Virtual Reality, Quantitative Imaging in Medicine and Surgery, Volume 1, Number 1, pages 11 to 16, January 2011. 64. D. Coffey, N. Malbrayton, T. B. Liu, I. Borisjani, F. Soteropoulos, A. G. Erdman, and D. F. Keefe, Interactive Slice WM. Navigating and interrogating volume data sets using a multi-surface. Multi-touch VR interface. IEEE Transactions on Visualization and Computer Graphics, Volume 18, Number 10, pages 1614 to 1626, October 2012. 65. J. G. Kirais, O. Aguilar, A. D. Liao, and A. G. Forbes, Immersive Analytics for Clinical Neuroscience, an Immersive Analytics Workshop, Phoenix, USA, 2017, pages 1 to 5. 66. D. Acevedo, E. Vogt, D. H. Laidlaw, and M. S. Jukowski, Archaeological Data Visualization in VR, Analysis of LAMP Finds at the Great Temple of Petra, a Case Study in Proc Conference on Visualization. San Diego, California, 2001, pages 493 to 496. 19. 67E. Vogt, D. A. Feliz, D. H. Laidlaw, and M. S. Jukowski, Discovering Petra, Archaeological Analysis in VR, IEEE Computer Graphics and Applications, Volume 22, Number 5, pages 38 to 50, September 2002. 68. N. G. Smith, K. Nab, C. DeFanti, P. Weber, J. Schulz, A. Prudhomme, F. Kuster, T. E. Levy, and T. A. DeFanti Artifact Vis 2, Managing Real-Time Archaeological Data in Immersive 3D Environments. In Digital Heritage, Marseille, October 2013, pages 363 to 370. 69. P. Saalfeld, J. Patschka, and B. Preem, an immersive system for exploring and measuring medical image data in Mensch UND Computergangsband, Regensburg, D. September 2017, pages 73 to 82. 70. B. F.R. Olich, S. Barris, B. Zenner, J. Plate, and M. G. Abel, Exploring Geoscientific Data in Virtual Environments in Proc Conference on Visualization, San Francisco, California, 1999. Pages 169 to 173. 71. J. C. Lombardo, a virtual reality environment for macromolecules exploration, virtual reality and prototyping, page 3, 1999. 72, M. Gahold, M. Falvo, W. Matthews, S. Paulson, S. Washburn, D. Erie, R. Superfine, F. Brooks and R. Taylor, IEEE/ASME Transactions on Mechatronics, Volume 5, Number 2. Pages 189 to 198, June 2000. 73. W. Chi, R. M. Taylor, C. G. Healy, and J. B. Martins, a comparison of immersive HMD, fish tank VR and fish tank with haptics displays for volume visualization, in Proc 3rd SYMP on Applied Perception in Graphics and Visualization, Boston, 2006, pages 51 to 58. 74. K. Nesbitt, interacting with stock market data in a virtual environment, in Proc Joint Eurographics IEEE TZG Symposium on Visualization, Ascona, Switzerland, 2001, pages 273 to 282. 75. A. Fonnet, F. Melky, Y. Pre-E, F. Picarone and G. Claquette, Immersive Data Exploration and Analysis in Student Interaction Design Research Conference, Helsinki, Finland, May 2018, pages 1 to 8. 76. P. Riepschel-Eger, B. K. Oskin, A. S. Mather, S. Gumhold, R. Majumdar, and R. Doxelt, Debug AR. Mixed-dimensional displays for immersive debugging of distributed systems. In Extended Abstracts Chi 2018, Montreal QC, Canada, 2018, pages 1 to 6. 77. A. Cantu, T. Duval, O. Grisford, and G. Koppen, Helovis. A helical visualization for SIGINT analysis in IEEE Pacific Viz 2018, Kobe, Japan, 2018, pages 1 to 6. 78. A. Moore, Infoticals, Information Modeling in Immersive Environments, in preceding 6th International Conference on Information Visualization, London, UK, 2002, pages 457 to 461. 79. T. Dis, M. Papka, R. Stevens, M. Pellegrino, and V. Taylor. Virtual reality visualization of parallel molecular dynamics simulation in a conference for high-performance computing, networking, storage, and analysis, San Diego, California, 1995, pages 1 to 5. 80. Z.int, Froelich, Molecular Dynamics Simulation in Virtual Environments, Computer Graphics Forum, Volume 17, Number 3, pages 267-273, August 1998. 81. G. Wesk, Three-Dimensional Visualization of Fluid Dynamics on the Responsive Workbench, Future Generation Computer Systems, Volume 15, Number 4, pages 469 to 475, July 1999. 82. A. Kageyama, Y. Tomura, and T. Sato. Visualization of Vector Field by Virtual Reality, Progress of Theoretical Physics Supplement, Volume 138, pages 665 to 673, April 2000. 83. M. Schursky, A. Jerndt, T. Van Riemerstel, T. Cullen, P. Adomate, O. Lang, S. Pischinger, and C. Bischoff, Vista FlowLib, a framework for interactive visualization and exploration of unsteady flows in virtual environments, in Workshop on Virtual Environments, Zurich, Switzerland, 2003, pages 77 to 85. 84, J. Sobel, A. Forsberg, D. Laidlaw, R. Zalesnik, D. Keefe, I. Pivkin, G. Karniadakis, P. Richardson, and S. Swartz, particle flurries, synoptic 3D pulsatile flow visualization, IEEE Computer Graphics and Applications, Volume 24, Number 2, pages 76 to 85, March 2004. 85, B. Henschel, I. Tejo, M. Probst, M. Walter, M. Baer, C. Bischoff, and T. Cullen. Interactive blood damage analysis for ventricular assist devices, IEEE Transactions on Visualization and Computer Graphics, Volume 14, Number 6, pages 1515 to 1522, November 2008. 86, W. L. Hibbard, J. Anderson, I. Foster, B. E. Paul, R. Jacob, C. Schaefer, and M. K. Tyree exploring coupled atmosphere-ocean models using VIS 5D, the International Journal of Supercomputer Applications and High-Performance Computing, Volume 10, No. 2 to 3, pages 211 to 222, June 1996. 87, V. Joswal, Savievis. Distributed real-time visualization of time-varying scalar and vector fields using the CAVE Virtual Reality Theater in Proc 8th Conference on Visualization, 1997, pages 301 to 308. 88, G. H. Wheelas, C. M. Lascara, J. Lee, A. Kapoor, A. E. Johnson, and T. A. Defanti. CAVE 6D, a tool for collaborative immersive visualization of environmental data in IEEE Visualization. Research Triangle Park, North Carolina, USA, 1998, pages 1 to 4. This article has been accepted for publication in a future issue of this journal, but has not been fully edited. Content may change prior to final publication. Citation information: DOI 10.1109/TVCG.2019.2929033, IE Journal OF TVCG, Volume 20, NO. X, month 2019. 89, K, S, Park, A, Kapoor, and J, Lee. Lessons learned from employing multiple perspectives in a collaborative virtual environment for visualizing scientific data in Proxy-on-F on collaborative virtual environments, San Francisco, USA, 2000, pages 73 to 82. 90, T. Oji, Y. Tadiyama, and S. Sato, Visual Data Mining in Immersive Virtual Environment based on 4K stereo images in INSEAN-F on Virtual and Mixed Reality, Berlin, 2009. Pages 472 to 481. 91, S. Sato, Y. Tadiyama, and T. Oji, Super High-Definition Three-Dimensional Display Environment Applied to Visual Data Mining in 13th in Conference on Network-Based Information Systems, September 2010, pages 414 to 419. 92, A. Kjellin, L. W. Pedersen, S. Seipel, and M. Lind, Different Levels of 3D, an Evaluation of Visualized Discrete Spatiotemporal Data in Spacetime Cubes, Information Visualization, Volume 9, Number 2, pages 152 to 164, January 2010. 93, M. Cordell, T. Dwyer, and C. Herder, Immersive Solutions for Future Air Traffic Control and Management, in Proc ACM Companion on Interactive Surfaces and Spaces, Niagara Falls, Ontario, Canada, 2016, pages 25 to 31. 94, H. Nguyen, F. Wong, R. Williams, U. Engelke, A. Kruger, and P. D'Souza, Immersive Visual Analysis of Insect Flight Behavior in Immersive Analytics Workshop, Phoenix, USA, 2017, pages 1 to 5. 95, M. Reddy, T. Dwyer, and J. H. Haga, Immersive Visualization of Big Data for River Disaster Management in Immersive Analytics Workshop, Phoenix, USA, 2017, pages 1 to 4. 96, A. Cunningham, J. Walsh, and B. H. Thomas, Immersive Visualization of Geotemporal Narratives in Law Enforcement in 4th International Symposium on Big Data, Visual and Immersive Analytics, Konstanz, Germany, 2018, pages 31 to 38. 97, Y. Yang, T. Dwyer, B. Jenny, K. Marriott, M. Cordell, and H. Chin. Origin-destination flow maps in immersive environments, IEEE Transactions on Visualization and Computer Graphics, 2018. 98, C. Herter, N. H. Reisch, S. M. Drucker, M. Cordell, R. Alagier, and R. Vuillamo, Fiberclay, Sculpting Three-Dimensional Trajectories to Reveal Structural Insights, IEEE Transactions on Visualization and Computer Graphics, 2018. 99, S. Bryson, Virtual Spacetime, An Environment for the Visualization of Curved Spacetimes via Geodesic Flows, in Proceedings of the Third Conference on Visualization 92, 1992. Pages 291 to 298. 100, J. A. Walsh, A. Cunningham, R. Smith, and B. H. Thomas. Tangible Braille Plot, Tangibly Exploring Geotemporal Data in Virtual Reality in 4th International Symposium on Big Data, Visual and Immersive Analytics, Konstanz, Germany, 2018. Pages 167 to 172. 101C. Helbig, H. S. Bauer, K. Rink, V. Wolfmeyer, M. Frank and O. Kolditz, Concept and Workflow for 3D Visualization of Atmospheric Data in a Virtual Reality Environment for Analytical Approaches, Environmental Earth Sciences. Volume 72, Number 10, pages 3767 to 3780, November 2014. 102, J. Szymanczyk, D. Cook, B. D. Kohlmeier, and C. Krusnera. Dynamic Statistical Graphics in the Cave Virtual Reality Environment in PROC, Dynamic Statistical Graphics Workshop, Volume 29, 1996, pages 41 to 47. 103, A. Amura, O. R. Zayin, and Y. G. Immersed Visual Data Mining, Walking the Walk, BNCOD, Volume 18, pages 202 to 218, 2001. 104, H. R. Nagel, E. Granum, and P. Museus, Methods for Visual Mining of Data in Virtual Reality, Proceedings of the International Workshop on Visual Data Mining, pages 13 to 27, 2001. 105, H. R. Nagel, M. Vitrup, E. Granum, and S. Bovjerg, Exploring Nonlinear Data Relationships in VR using the 3D Visual Data Mining System in 3rd INT Workshop on Visual Data Mining, Melbourne, Florida, U.S., 2003, pages 133 to 150. 106, H. Azag, F. Picarone, C. Goynot, and G. Venturini VR Miner, a tool for multimedia database mining with virtual reality, processing and managing complex data for decision support. Pages 318 to 339, 2006. 107, B. S. Megans, R. M. C. Ducarmo, L. Almeida, A. S. Goncalves, S. C. V. Pinheiro, M. De Brito Garcia, and P. I. A. Godinho. Multidimensional information visualization using augmented reality in PROC Conference on Virtual Reality Continuum and its applications, Hong Kong, China, 2006, pages 391 to 394. 108. H. R. Nagel, E. Granum, S. Bovjerg and M. Vitrup, Immersive Visual Data Mining, the 3D approach in visual data mining, Berlin, Heidelberg, 2008, pages 281 to 311. 109C. Donalek, S. G. Georgovsky, A. Syok, A. Wang, J. Zhang, E. Lawler, S. Ya, A. Mahaval, M. Graham, A. Drake, S. Davidoff, J. S. Norris and G. Longo, Immersive and Collaborative Data. 20. Visualization using virtual reality platforms in PROC Big Data, Washington, D.C., USA, October 2014, pages 609 to 614. 110. S. Butcher, S. Hubenschmid, J. M. Euler, J. Fuchs, and H. Reiterer. Clusters, Trends, and Outliers. How immersive technologies can facilitate the collaborative analysis of multidimensional data in Extended Abstracts Chi 18, Montreal QC, Canada, 2018. 111. I. Rojdestensky, D. Majeska, F. Pedersen, M. Rojdestvenskia, and P. Gustafsson, Sequence World, a genetics database in virtual reality in PROC Information Visualization, London, UK, 2000, pages 513 to 517. 112. D. Wijayasekara, O. Linda, and M. Manik, KVSOM. Immersive visual data mining using 3D self-organizing maps in the 2011 International Joint Conference on Neural Networks, San Jose, California, USA, July 2011, pages 2471 to 2478. 113. K. Einsfeld, S. Aney, M. Deller, A. Ebert, B. Klein, and C. Rieschling, Dynamic Visualization and Navigation of Semantic Virtual Environments in PROC Information Visualization, London, UK, 2006, pages 569 to 574. 114. D. Felcher, M. Billinghurst, S. Hayes, and R. Stiles, using augmented reality for visualizing complex graphs in 3 dimensions, in PROC 2nd IEEE and ACM in Symposium on Mixed and Augmented Reality, Tokyo, Japan, 2003, pages 84 to 93. 115. N. F. Airy, P. E. Groh, J. H. Arison, and R. Gerby, Visual Data Mining of Genomic Databases by Immersive Graph-Based Exploration in Graphite 05, Dunedin, NZ, 2005, pages 143 to 146. 116. J. A. Henry and N. F. Polys, The Effects of Immersion and Navigation on the Acquisition of Spatial Knowledge of Abstract Data Networks, Procedia Computer Science, Volume 1, Number 1, pages 17371-746, May 2010. 117. D. Zalasko, S. Horn, S. Freitag, B. Weyers, and T. W. Cullen. Evaluation of hands-free HMD-based navigation techniques for immersive data analysis in PROC Virtual Reality, Greenville, South Carolina, March 2016, pages 317 to 318. 118 P. Young and M. Monroe, Visualizing Software in Virtual Reality, in Proc 6th and Workshop on Program Comprehension. IWPC 98, Ischia, Italy, 1998, pages 19 to 26. 119 C. Knight and M. Monroe, Comprehension within Virtual Environment Visualizations, in Proc 7th Workshop on Program Comprehension, Pittsburgh, Pennsylvania, USA, 1999. Pages 4 to 11. 120 Virtual but Visible Software, in Proc at Conference on Information Visualization, London, UK, 2000, pages 198 to 205. 121 C. Russo dos Santos, P. Grow, P. Abel, D. Loisel, N. Tricod, and J. Paris, Mapping Information onto 3D Virtual Worlds, in Proc-CONF on Information Visualization, London, UK, 2000, pages 379 to 386. 122 J. I. Mailtick, J. Lee, A. Marcus, and G. Dunlap, Visualizing Object-Oriented Software in Virtual Reality, in Proc 9th International Workshop on Program Comprehension, 2001, pages 26 to 35. 123 J. I. Mailtick, J. Lee, and A. Marcus, Visualizing Software in an Immersive Virtual Reality Environment, in Proceedings of ICC, Toronto, Canada, 2001, pages 12 to 17. 124 R. Souza, B. Silva, T. Mendez, and M. Mendonc A. Skyscraper, an augmented reality visualization for software evolution, in Proc of Second Brazilian Workshop on Software Visualization, Natal, Brazil, 2012, pages 1 to 8. 125 F. Fitka, A. Kraus, and W. Hasselbring, Exploring Software Cities in Virtual Reality, in Third Working Conference on Software Visualization, Bremen, Germany, September 2015. Pages 130 to 134. 126. Software Landscape and Application Visualization for System Comprehension with Explorviz, Information and Software Technology, Volume 87, pages 259 to 277, July 2016. 127 U. Lechner, L. Nelson, D. Cook, S. Pearson, and J. Simanzik. Using dynamic statistical graphics in a highly immersive virtual reality environment to understand multivariate, spatial, data, Bulletin of the International Statistical Institute, 51st Session Istanbul, 1997, Volume 2, pages 31 to 34, 1997. 128 S. Zhang, C. Demiralp, D. Keefe, M. De Silva, D. Laidlaw, B. Greenberg, P. Basser, C. Perpali, E. Kayaka, and T. Dijsboek, an immersive virtual environment for DTMRI volume visualization applications, a case study in Proc Visualization, San Diego, California, USA, 2001. Pages 437 to 441. 129 M. Cordell, A. Cunningham, T. Dwyer, B. H. Thomas, and K. Marriott, IMAXs, immersive axes as embodied affordances for interactive multivariate data visualization in ProcUSD, Chuabec, QC, Canada, 2017, pages 71 to 83. 130 R. J. Garcia Hernandez, C. Andes, M. Weidman, and D. Kranzmuller, Perspectives for Using Virtual Reality to Extend Visual. This article has been accepted for publication in a future issue of this journal, but has not been fully edited. Content may change prior to final publication. Citation information: DOI 10.1109/TVCG.2019.2929033, i.e. Journal OF TVCG, Volume 20, NO. X, month 2019. Data Mining and Information Visualization in 2016 IEEE Aerospace Conference, Big Sky, Montana, USA, March 2016, pages 1 to 11. 131, N. Sawant, C. Sharver, J. Lee, A. Johnson, G. Reinhardt, E. Creel, S. Bachu, S. Bailey, and R. Grossman, The Teleimmersive Data Explorer. A distributed architecture for collaborative, interactive visualization of large datasets in 4th International Immersive Projection Technology Workshop, Iowa, USA, 2000, pages 1 to 16. 132, B. Patnaik, A. Batch, and N. Elmquist, Information Olfactation, Harnessing Scent to Convey Data, IEEE Transactions on Visualization and Computer Graphics, 2018. 133, B. Yost and C. North, The Perceptual Scalability of Visualization, IEEE Transactions on Visualization and Computer Graphics, Volume 12, Number 5, pages 837 to 844, September 2006. 134, B. Jackson, Tung Yuan Lau, D. Schroeder, K. C. Toussaint, and D. F. Keefe, a lightweight, tangible 3D interface for interactive visualization of thin fiber structures. IEEE Transactions on Visualizations and Computer Graphics, Volume 19, Number 12, pages 280 to 2809, December 2013. 135, K. Kim, B. Jackson, I. Karamuzas, M. Adiagbo, S. J. Guy, R. Graf, and D. F. Keefe Bima, a multimodal interface for expert experiential analysis of political assemblies at the Knicks in ancient Greece, in 2015 IEEE Symposium on 3D User Interfaces, 3DUI. Alls, France, IEEE, March 2015, pages 19 to 26. 136, N. Brunhart Lupo, B. W. Bush, K. Grachala, and S. Smith. Simulation Exploration through Immersive Parallel Planes in Workshop Immersive Analytics, Greenville, South Carolina, March 2016, pages 19 to 24. 137, A. Masrer, J. Zhao, J. O. Walgren, P. Lefemina, and A. Klippel. Immersive Applications for Informal and Interactive Learning for Earth Sciences in Immersive Analytics Workshop, Phoenix, USA, 2017, pages 1 to 5. 138, D. F. Keefe, A. Gupta, D. Feldman, J. V. Carlos, S. Krabiel Keefe, and T. J. Griffin, Scaling Up Multi-Touch Selection and Querying. Interfaces and applications for combining mobile multi-touch input with large-scale visualization displays, International Journal of Human-Computer Studies, Volume 70, Number 10. Pages 703 to 713, October 2012. 139, D. Song and M. L. Norman, Cosmic Explorer, a virtual reality environment for exploring cosmic data in Proc Research Properties in Virtual Reality Symposium, 1993, pages 75 to 79. 140, M. Kutek, Scientific Visualization in Virtual Reality, Interaction Techniques and Application Development, PhD dissertation, Delft University of Technology, 2003. 141. B. Henschel, M. Walter, and T. Cullen, Virtual Reality-Based Multi-View Visualization of Time-Dependent Simulation Data in 2009 IEEE VR Conference, LA, USA. March 2009, pages 253 to 254. 142. R. C. R. Moda and J. D. Silva, 3D interactive lenses for visualization in virtual environments in IEEE Civis 2018. Short paper session, no. October, Berlin, Germany, 2018, pages 1 to 5. 143. E. Maffoud and A. Liu, Gaze-Directed Immersive Visualization of Scientific Ensembles in Proc ACM Companion on Interactive Surfaces and Spaces, 2016, pages 77 to 82. 144. S. Bong-Artner, A. Ebert, M. Deller, and S. Aney, 2D meets 3D, a human-centered interface for visual data exploration in Extended Abstracts Chi, San Jose, California, USA, 2007, pages 2273 to 2278. 145. H. Ijang, T. Fujiwara, L. Yunxian, L. Wenqi, and M. Quanlu, a gesture system for graph visualization in virtual reality environments in Proc Pacific Vis, Seoul, South Korea, April 2017, pages 41 to 45. 146. V. Gertman, P. Olsoi, N. Glenn, and A. Joshi, RSVP, Remote Sensing Visualization Platform for Data Fusion. In workshop, Immersive Visualization Revisited Challenges and Opportunities at IEEE VR 2012, Costa Mesa, California, US, 2012, pages 1 to 5. 147. M. Simpson, J. O. Walgren, A. Klippel, L. Yang, G. Garner, K. Keller, D. Adrien, and S. Bunsel, Immersive Analytics for Multi-Objective Dynamic Integrated Climate Economy, DICE, Models. In Proc ACM Companion on Interactive Surfaces and Spaces, Niagara Falls, Ontario, Canada, 2016, pages 99 to 105. 148. C. Herder, N. H. Reish, M. Pahud, E. Ofek, S. Drucker, B. Lee, D. Brown, and C. Wang into the mixed reality data sphere, mapping users' movements to data exploration tools. In Immersive Analytics Workshop, Phoenix, USA, 2017, pages 1 to 4. 149. D. Zelasco, M. Belgart, A. Meissner, M. Hege, B. Henschel, B. Weyers, and T. W. Cullen, Bueno SDIAs, supporting desktop immersive analytics while actively preventing cyber sickness. Immersive Analytics Workshop, Phoenix, USA, 2017, pages 1 to 4. 150. P. Morse, A. Reading, C. Lug, and S. Kendurden, Tagger VR, Interactive Data Analytics for Geoscience, a novel interface for interactive visual analytics of large geoscientific datasets. 21. In Cloud Repositories, in Proc Big Data Visual Analytics, Hobart, TAS, Australia, September 2015, pages 1 to 2. 151. M. Drouhard, C. A. Steed, S. Hahn, T. Profin, J. Daniel, and M. Matheson, Immersive Visualization for Materials Science Data Analysis using the Oculus Rift in Big Data, Santa Clara, California, USA, October 2015, pages 2453 to 2461. 152 C. A. Steed J. Daniel M. Drouhard S. Hahn and T. Profen. Immersive Visual Analytics for Transformative Neutron Scattering Science in Workshop on Immersive Analytics, Greenville, South Carolina, March 2016, pages 38 to 43. 153 B. Laha, D. A. Bowman, D. H. Laidlaw and J. J. Sosha, a classification of user tasks in visual analysis of volume data in IEEE Scientific Visualization Conference, SciVis. Chicago, Illinois, USA, IEEE, October 2015, pages 1 to 8. 154 D. F. Keefe and T. Eisenberg, Reimagining the Scientific Visualization Interaction Paradigm, Computer, Volume 46, Number 5, pages 51 to 57, May 2013. 155 S. K. Badam, A. Srinivasan, N. Elmqvist and J. Stasko, Affordances of Input Modalities for Visual Data Exploration in Immersive Environments, in Immersive Analytics Workshop, Phoenix, USA, 2017, pages 1 to 5. 156 W. B. Uskal, J. Chin, R. Doxelt, S. Drucker, T. Dwyer, T. G. Org, T. Eisenberg, A. Karen, C. North, and W. Sturzlinger, Interaction for Immersive Analytics, in Immersive Analytics, 2018, pages 95138. 157 K. Marriott, F. Schreiber, T. Dwyer, K. Klein, N. H. Reisch, T. Ito, W. Sturzlinger, and B. H. Thomas, eds. Immersive Analytics, SARE. Lecture Notes in Computer Science. Springer, 2018, Volume 11190. 158 G. Claquette, M. Pereira, F. Picarone, Y. Pre-E and T. Vidger, Towards HMD-Based Immersive Analytics, in Immersive Analytics Workshop, Phoenix, USA, 2017, pages 1 to 5. 159 M. Billinghurst, M. Cordell, A. Bazarianos, and T. Margolis, Collaborative Immersive Analytics, in Immersive Analytics, 2018, pages 221 to 257. 160 G. E. Marai, A. G. Forbes, and A. Johnson, Interdisciplinary Immersive Analytics at the Electronic Visualization Laboratory, Lessons Learned and Upcoming Challenges, in Workshop on Immersive Analytics, Greenville, South Carolina, USA, March 2016, pages 54 to 59. 161 S. Boneta, R. Veris, and C. Collins, Personalized Views for Immersive Analytics, in ACM Companion on Interactive Surfaces and Spaces, Niagara Falls, Ontario, Canada, 2016, pages 83 to 89. 162 H. Nguyen, P. Marandy, and U. Engelke, Collaborative Framework Design for Immersive Analytics, in Big Data Visual Analytics, Sydney, NSW, Australia, November 2016, pages 1 to 8. 163 I. Herman, G. Melankin, and M. Marshall, Graph Visualization and Navigation in Information Visualization, a Survey, IEEE Transactions and Visualizations for Computer Graphics, Volume 6, Number 1, pages 24 to 43, 2000. 164C, where and G, Frank, viewing a graph in a virtual reality display is 3 times as good as a 2D diagram in Proxymposium on Visual Languages, St. Louis, Missouri, USA, 1994. Pages 182 to 183. 165. Evaluating stereo and motion cues for visualizing information nets in 3 dimensions. ACM Transactions on Graphics, Volume 15, Number 2, pages 121 to 140. April 1996. 166C, Ware and P. Mitchell, Visualizing Graphs in 3 Dimensions. ACM Transactions on Applied Perception, Volume 5, Number 1, pages 1 to 15, January 2008. 167. N. Grefford, F. Picarone and P. Kuntz, Visual Community Detection, an evaluation of 2D, 3D perspective and 3D stereoscopic displays, an international symposium on graph drawing. Eindhoven, the Netherlands, 2011, pages 215 to 225. 168. F. Samavati, K. Hockey, S. Skirbo, N. F. Polys, M. Sitara, and B. D. Jones, the effects of display fidelity, visual complexity, and task scope on spatial understanding of 3D graphs in Proc Graphics Interface, Regina, Saskatchewan, Canada, 2013, pages 25 to 32. 169. B. Schneiderman, Why Not Make Interfaces Better Than 3D Reality? IEEE Computer Graphics and Applications, Volume 23, Number 6, pages 12 to 15, November 2003. 170. C. D. Wickens, D. H. Merwin and E. L. Lin, Implications of Graphics Enhancements for the Visualization of Scientific Data, Dimensional Integrality, Stereopsis, Motion, and Mesh Human Factors. The Journal of the Human Factors and Ergonomics Society, Volume 36, Number 1, pages 44 to 61, March 1994. 171. D. Asimov, The Grand Tour, a tool for viewing multidimensional data, Siam Journal on Scientific and Statistical Computing, Volume 6, Number 1. Pages 128 to 143, January 1985. This article has been accepted for publication in a future issue of this journal, but has not been fully edited. Content may change prior to final publication. Citation information: DOI 10.1109/TVCG.2019.2929033, i.e. Journal OF TVCG, Volume 20, NO. X, month 2019. 172. L. Nelson, D. Cook, and C. Krusnera, Scobie versus the C2, Results of an Experiment Comparing Data Visualization in a 3D Immersive Virtual Reality Environment with a 2D Workstation Display. Computational Statistics, Volume 1, pages 39 to 52, 1999. 173. D. Raja, D. A. Bowman, J. Lucas, and C. North, Exploring the Benefits of Immersion in Abstract Information Visualization, Proc 8th Immersive Projection Technology Workshop, pages 61 to 69, 2004. 174. J. A. W. Filio, M. F. Ray, C. M. Freitas, and L. Nettle, Immersive Analytics of Dimensionally Reduced Data Scatterplots, an Immersive Analytics Workshop, Phoenix, USA, 2017, pages 1 to 5. 175. B. Bach, R. Sickett, J. Bayer, M. Chordal, and H. Pfister, the hologram in my hand. How effective is interactive exploration of 3D visualizations in immersive tangible augmented reality? IEEE Transactions on Visualization and Computer Graphics, Volume 24, Number 1, pages 457 to 467, January 2018. 176K, Grachala, Immersive Well Path Editing, Investigating the Added Value of Immersion in IEEE Virtual Reality, Chicago, Illinois, USA, 2004. Pages 157 to 164. 177, P. Shakart and D. A. Bowman, The Benefits of Immersion for Spatial Understanding of Complex Underground Cave Systems in Proc ACM Symposium on Virtual Reality Software and Technology, Newport Beach, California, 2007, pages 121 to 124. 178, E. D. Reagan, R. Copper, P. Shakart, and D. A. Bowman. Studying the effects of stereo, head tracking, and field of regard on a small-scale spatial judgment task, IEEE Trans on Visualization and Computer Graphics, Volume 19, Number 5. Pages 886 to 896, 2013. 179, V. W. Van Schuten, E. M. A. G. Van Dyke, E. Zudalovasainstra, A. Suanesiaputra, and J. H. C. Reiber. The Effect of Stereoscopy and Motion Cues on 3D Interpretation Task Performance in INSA-NF on Advanced Visual Interfaces, Roma, Italy, 2010, pages 167 to 170. 180, E. D. Reagan, A. Wood, R. P. McMahon, and D. A. Bowman. Trade-offs related to travel techniques and level of display fidelity in virtual data analysis environments in Joint Virtual Reality Conference of ICTGV, Madrid, Spain, 2012, pages 1 to 4. 181, B. Laha, K. Sisharma, J. D. Schiffbauer, and D. A. Bowman. Effects of Immersion on Visual Analysis of Volume Data, IEEE Transactions on Visualization and Computer Graphics, Volume 18, Number 4, pages 597 to 606, April 2012. 182, B. Laha, D. A. Bowman, and J. J. Sosha, Effects of VR System Fidelity on Analyzing Isosurface Visualization of Volume Datasets, IEEE Transactions on Visualization and Computer Graphics, Volume 20, Number 4, pages 513 to 522, April 2014. 183, Prabhat, A. Forsberg, M. Katsurin, K. Wharton, and M. Slater. A comparative study of desktop, fish tank, and cave systems for the exploration of volume-rendered confocal datasets, IEEE Transactions on Visualization and Computer Graphics, Volume 14, Number 3, pages 551 to 563, May 2008. 184, J. Chin, H. Kai, A. P. Ochis, and D. H. Laidlaw, Effects of Stereo and Screen Size on the Legibility of Three-Dimensional Stream Tube Visualization. IEEE Transactions on Visualization and Computer Graphics, Volume 18, Number 12, pages 2130 to 2139, December 2012. 185, C. Demiralp, C. Jackson, D. Karolitz, S. Zhang, and D. Laidlaw. Cave and fish tank virtual reality displays, a qualitative and quantitative comparison, IEEE Transactions on Visualization and Computer Graphics, Volume 12, Number 3, pages 323, 330, 2006. 186, B. Laha, D. A. Bowman and J. D. Schiffbauer, validation of the MR simulation approach for evaluating the effects of immersion on visual analysis of volume data. IEEE Trans on Visualization and Computer Graphics, Volume 19, Number 4, pages 529 to 538, April 2013. 187, M. Cordell, T. Dwyer, K. Klein, B. Laha, K. Marriott, and B. H. Thomas, Immersive Collaborative Analysis of Network Connectivity, Cave-Style or Head-Mounted Display? IEEE Transactions on Visualization and Computer Graphics, Volume 23, Number 1, pages 441 to 450, January 2017. 188, L. Marino, J. Fuchs, M. Blumenschein, C. Anslow, M. Ghaffari, O. Neerstress, M. Barish, and D. A. Keim on the impact of the medium in the effectiveness of 3D software visualizations in Vsoft, Shanghai, China, September 2017, pages 11 to 21. 189, M. Simpson, J. Zhao, and A. Klippel, Take a Walk, Evaluating Movement Types for Data Visualization in Immersive VR in Immersive Analytics Workshop, Phoenix, USA, 2017, pages 1 to 5. 190, W. Biaskol, P. Riepschel-Ager, R. Langner, and R. Doxelt, Investigating the Use of Spatial Interaction for 3D Data Visualization on Mobile Devices in PROC Interactive Surfaces and Spaces. Brighton, United Kingdom, ACM Press, 2017, pages 62 to 71. 191A, Drogemuller, A. Cunningham, J. Walsh, M. Cordell, W. Ross, and B. H. Thomas, Evaluating Navigation Techniques for 3D. 22. Graph Visualizations in Virtual Reality in 4th International Symposium on Big Data, Visual and Immersive Analytics, Konstanz, Germany, 2018, pages 50 to 59. 192, A. Fonnet, T. Vigier, G. Claquette, F. Picarone, and Y. Pre-E Axes and Coordinate Systems Representations for Immersive Analytics of Multidimensional Data in 4th International Symposium on Big Data, Visual and Immersive Analytics, Konstanz, Germany, 2018, pages 91 to 100. 193 S. Bryson, S. Johann and L. Schlecht, An Extensible Interactive Visualization Framework for the Virtual Wind Tunnel in PROC International Symposium on Virtual Reality, Albuquerque, New Mexico, USA, 1997, pages 106 to 113. 194 A. Ahmed, T. Dwyer, M. Forster, X. Fu, J. Ho, S. H. Hong, D. Koshutsky, C. Murray, N. S. Nikolov, R. Tabe, A. Tarasov, and K. Su, Geomi, Geometry for Maximum Insight in Graph Drawing, Limerick, Ireland, 2006, pages 468 to 479. 195, R. Grissett, A. Maloney, M. Billinghurst, and D. Schmalstieg. Navigation Techniques in Augmented and Mixed Reality, Crossing the Virtuality Continuum in Handbook of Augmented Reality. Springer, New York, 2011, ch20, pages 379 to 407. 196 F. Argelagat, and C. Andujar, A Survey of 3D Object Selection Techniques for Virtual Environments, Computers and Graphics, Volume 37, Number 3, Pages 121 to 136, May 2013. 197, J, Laviola, E, Cruich, R, P, McMahon, D, A, Bowman, and I, Pupirev, 3D User Interfaces, Theory and Practice. Redwood City, California, USA, Addison Wesley, 2017. 198, R, Sadna, V, Settler, and J, Stasko, Redefining a Contribution for Immersive Visualization Research, in Proc ACM Companion on Interactive Surfaces and Spaces, Niagara Falls, Ontario, Canada. 2016, pages 41 to 45. 199, IMAXs. http://github.com/maximecorddeal/IMAXs, July 20th, 2018. 200, R, Sickett, J, Lee, J, Y, Choi, M, Cordell, W, K, Jong, V, Bach, and H, Pfister, DXR, a toolkit for building immersive data visualizations, IEEE Trans on Visualization and Computer Graphics, 2018. 201, IDK, Immersive Analytics Toolkit, https://github.com/maximecorddeal/IDK, accessed December 17th, 2018. 202, Virtualytics, http://www.virtualytics.com/ accessed 2018 to 0720. 203A, Irlidi, S, Vonetstein, L, Alum, and B, Thomas, Tangible Interaction Techniques to Support Asynchronous Collaboration, an In-Symposium on Mixed and Augmented Reality, ISMAR, Adelaide, SA, Australia. October 2013, pages 1 to 6. 204A, Nazsani, H, by G. Lee and M, Billinghurst, Taggett, AR annotation using wearable sensors in SIGGRAPH Asia 2015 mobile graphics and interactive applications on SA15. Kobe, Japan, ACM Press, 2015, pages 1 to 4. 205, E. A. Wernert, W. R. Sherman, P. O'Leary, and E. Whiting, A Common Path Forward for the Immersive Visualization Community. In Workshop Immersive Visualization Revisited Challenges and Opportunities at IEEE VR 2012, Costa Mesa, California, US, 2012, pages 1 to 8. 206, D. Keefe, D. Acevedo, J. Miles, F. Drury, S. Swartz, and D. Laidlaw, Scientific Sketching for Collaborative VR Visualization Design, IEEE Transactions on Visualization and Computer Graphics, Volume 14, Number 4, pages 835 to 847, July 2008. 207, R. Hackathorn and T. Margolis, Immersive Analytics, Building Virtual Data Worlds for Collaborative Decision Support, in Workshop on Immersive Analytics, Greenville, South Carolina, March 2016, pages 44 to 47. Adrien Fonnet is a PhD student investigating immersive analytics at Nantes University, France. He holds an engineering degree of digital mockup and virtual reality. He became interested in data analysis during his 2 years as a master data expert in an international agribusiness group and consolidated his skills in virtual and augmented reality technology by working for a year as a research engineer for the Computer Graphics Center in Guimarães, Portugal. Yannick Pree holds an engineering degree in computer science, a master's degree in artificial intelligence and cognitive science, and a PhD in computer science. He is currently a professor of computer science at Nantes University. His research interests include human-computer interaction, information visualization, and user experience, with a focus on interdisciplinary approaches for the study of human-machine coupling and co-development.